Hello, and welcome everyone to this podcast for genetics. In this podcast, we're going to talk about probabilities and chi-square. In genetics, we often will use probabilities to make predictions. And then we'll do the experiment, and then finally we'll compare our observations with our predictions. So in this podcast, we're going to talk about the different probability tools that we're going to use to make these predictions. And then we're going to talk about how we're going to compare these our observations with our predictions using something called a chi-square analysis. There are going to be two probability tools that we're going to use. The first is the multiplication rule, and the other is the addition rule. I'm going to see if we can put these both on the same board here so we can compare them and see how we use them. Okay, the multiplication rule. It's when we look at the probability of two or more independent events occurring together. So to determine if two or more independent events are occurring together, you take each independent probability and multiply them. All right, we'll come back to the multiplication rule in just a moment, but now let's think about the addition rule. The addition rule is the probability of two or more mutually exclusive events occur together. When we say mutually exclusive, that means if you have two choices, that if one happens, then the other can't happen. That's what we mean when we say mutually exclusive. One event will exclude the other events from occurring. To calculate using this addition rule, we take each individual probability and add them. So let's take a simple example and talk about how we can apply the multiplication and the addition rule. And let's think about a coin toss. We know that if we have a coin and we flip it, that it will land on heads 50% of the time. So we're going to put it at 0.5. And we know it will land on tails 50% of the time. So when we talk about probability, we say 0.5. I should take a moment just to go back and say something about probability. A probability of 0 means there is an impossibility that that event will occur. Probability of 1 means there is a certainty that that event will occur. So when you report a probability, you should use values between 0 and 1. Okay, so let's use this simple example of tossing a coin to understand the probability of flipping the coin twice and getting tails each time. Another way you can think about this is, what's the probability of getting a tail on one toss and a tail on the second cross? Anytime we see a problem with the word "and" in it, that's a clue that we should be using the multiplication rule. So let's calculate this then. The probability of getting a tail on the first cross is 1/2. And then the probability of getting a tails on the second cross is also 1/2. And so then that equals 0.25. So the probability of getting tails on two successive crosses will be 0.25. Now let's spend just a few seconds here talking about why this is a use for the multiplication rule. Each of these events, flipping a coin once and then twice, are each independent. One of them does not have anything to do with the next. Interestingly, both times I flipped that coin, I got two heads. We'll see later when we talk about chi-square that just flipping a coin twice isn't a really good measure of this probability. You really need to flip it many times, hundreds of times, to really get close to that 0.5. All right, again, multiplication rule because each of these events are independent. Now let's think about the addition rule. Addition rule will help us solve a problem like this. What's the probability of tossing a coin one time and getting a heads or a tail? The key to this question is the word "or," just like we see "and" over here. "Or" is the signal that we're going to use the addition rule. Now, I suspect you could probably solve this problem without doing advanced probability analysis. We know if we flip a coin, you're going to get heads or tails. But it's a good, simple explanation of what's going on here. So here, it's the probability of getting heads or tails. We take a look at each event, and each one of occurring is 0.5. The word "or" implies the addition rule will be used, and so we will add these together. 0.5 plus 0.5 is equal to 1. So shockingly, every time we flip a coin, we are certain we will get a heads or a tail. Now, if you don't, then you know you're dealing with a mischievous coin, I suspect. Let's talk about why this applies to the addition rule. One of the distinctions between the addition rule and the multiplication rule is the addition rule deals with one event. In this case, the event is tossing the coin one time. The multiplication rule talks about two or more independent events. So one event, two events, or more events, I should say. They're also mutually exclusive. If you flip a coin one time and it's heads, it excludes the possibility that it could also be tails. Mutually exclusive means you can't flip a coin and you get heads and tails, one or the other. Let's now consider one of Mendel's crosses. And we'll stick with our favorite cross here, big R, little r times big R, little r. So let's use the multiplication rule with this monohybrid cross. What's the probability of getting a round seed plant and a wrinkled seeded plant? Again, we see this word and, so that's a cue that we're going to use the multiplication rule. And so the probability of getting a rounded seeded plant is 3/4. And the probability of getting a wrinkled seeded plant is 1/4. If you're unclear where we came up with those numbers, remember, just do a simple Punnett square up here. And we see these three here, out of the four, will be round seeds, and this one will be wrinkled seeds. It's the multiplication rule, so we're going to multiply these together. So the probability of getting a rounded seeded plant in one event and then a wrinkled seeded plant in the next event will be 3/16. Just to remind you, when we multiply fractions, the denominators do not have to be the same, and we just multiply them. So 3 times 16. I'll remind you when we get to the addition rule over here that we handle these fractions a little differently, just as a very quick refresher. All right, now let's use the addition rule for this same cross here, and let's ask this question. What's the probability that in a single event, we'll say crossing event, that a progeny will be heterozygous or homozygous dominant? Now we're looking at one plant, so it cannot be both heterozygous and homozygous dominant. They are mutually exclusive to each other. So the probability of being heterozygous is 2/4. It's these two out of the total of 4. So it's going to be 2/4, 1/4. So this being the addition rule, we're going to add these fractions. Remember, when we add fractions, the denominators have to be the same. And then in the result here, it's also going to be the same. We don't add the denominators together. Then 2 plus 1, we add those, and that's 3/4. So the probability that these two mutually exclusive events will occur, either a heterozygote or a homozygous dominant, is 3/4. A quick note, earlier in the podcast I said that when we report a probability, we should report it from 0 to 1. In this problem here, I've been using fractions. I think it's easier, at least for me, to work with fractions when I'm doing simple multiplication and additions. And then when we move on in a little bit, talk about the binomial expansion, I prefer to work with fractions. So I'm okay with you working with fractions here, but if you're asked to report a probability, you should give it to me in the probability. So in this case, it would be 0.75. And in this case, it would be 0.188. So let's work through an example. And let's consider an example of the recessive trait of Tay-Sachs. So with Tay-Sachs, let's provide some alleles. So T is the dominant allele, and little t is the recessive allele. Since T is dominant, we know that big T, or big T, whereas little t will have Tay-Sachs. Whereas little t, call it that, big T with the dash under it. So in this problem here, we're going to take two parents who are heterozygous. So they're both big T, little t. Whereas little t, so the question is, what's the probability that they will have 3 kids, each with Tay-Sachs? These are going to be independent events, so we can think of this as saying, what's the probability that the first kid will have Tay-Sachs, and then the second kid will have Tay-Sachs, and then the third kid will have Tay-Sachs. Each of them are independent. They do not influence one or the other events. So if the first kid has Tay-Sachs, that probability is 1/4. It's 0.25, but I'm going to work with fractions here. If the second kid has Tay-Sachs, there's a 1/4 chance. And then if the third kid has Tay-Sachs, it's also a 1/4. Again, we're going to apply the multiplication rule because these are independent events. So the probability that they're going to have 3 kids with Tay-Sachs is 1/64. Now, if I were to ask you, what's the probability that their next child will have Tay-Sachs? That, again, is going to be 1/4. Each new event is going to be independent. So each new event will be 1/4, or 3/4 if we ask what's the probability that it will be healthy. Okay, let's make it a little bit more complicated now. And let's ask, what's the probability that they will have 3 kids, of which 1 has Tay-Sachs and 2 are healthy? To calculate this problem, we're going to have to apply both the multiplication and the addition rule. If you want to, you can hit pause now and see if you can calculate this on your own. And then come back and you'll see what the result is, see if you got it right. Now, a common mistake when you have this kind of problem is that sometimes a student might say the probability of having a kid with Tay-Sachs is 1/4. The probability that the next kid does not have Tay-Sachs is 3/4. And then the probability that the third kid does not have Tay-Sachs is also 3/4. And just to remind you, in case you're not sure where we're coming up with these numbers, this is just a Punnett square, like we've been doing. These are our two parents, big T, big T, big T, little t, big T, little t, little t, little t. So these three out of the four will be healthy. All right. So if you did this, you would have got 9/64. And while this is partially true, it's not the correct answer. Because remember, this is not the only order that you could have the kids. It's possible that the first kid was healthy, and then the second kid had Tay-Sachs, and then the third kid was healthy. Probability of that occurring is 9/64. It's also possible that the first two kids were healthy, and the last kid had Tay-Sachs. This is also a 9/64 chance of happening. Each of these events can occur. However, they cannot occur at the same time. This event is mutually exclusive of these two. This one's mutually exclusive of these two, and this one's mutually exclusive of these two. But since they're all probable, we have to apply the addition rule, because they're mutually exclusive. So it's 9/64 plus 9/64 plus 9/64. And so that's going to equal 27/64. And so as a probability, you would say there is a 0.42 chance that this could occur, that they would have 3 children, 2 healthy and 1 with Tay-Sachs. So doing this, it's not so bad. You can figure out all the combinations with 3 kids. But what if you had more? What if you had 5 or 6 or 7 kids? It would be more difficult to figure out all the different combinations. You could do it, but it would take a little bit more time. And then if you get to up to 8, 10, 12 kids, then it becomes very cumbersome to do it this way. So another way you could do this is using the binomial expansion. And yes, I guess this means that when some of us told our algebra teacher that we would never use algebra in the real world, we were wrong. Because this is coming back to some of our algebra days. So we're going to make this even more complicated. We're going to have 5 kids. And of these 5 kids, 2 will have Tay-Sachs, and 3 will be healthy. So we're going to use our good friend from way back when, the binomial expansion. And remember, the binomial expansion is P plus Q raised to N. Sometimes you might see it as A plus B raised to the N. We'll primarily use P plus Q. So let's expand this binomial here to answer this question. And in answering this question, we want to think about every possibility that these two parents could have 5 kids, and different combinations with and without Tay-Sachs. And so let's define P here as being the probability that progeny will be healthy. And we know that in any individual event, that is going to be 3/4, or 0.75. Q is the probability that progeny will have Tay-Sachs. And we know that's going to be 0.25, or 1/4. So let's think about it this way for now. These parents could have 5 kids that are all healthy. They could also have 4 kids that are healthy and 1 kid who is not healthy. Or they could have 3 healthy kids and 2 kids with Tay-Sachs. You could also have 2 kids healthy, 3 kids with Tay-Sachs. You could also have 1 healthy kid, 4 with Tay-Sachs. Or you could have all kids with Tay-Sachs. Now the reason I put blanks in front of each of these is because we're going to put a number here that reflects the number of different ways you could have 4 kids without Tay-Sachs and 1 kid with. Or this one, the number of different combinations that you could have 3 healthy kids and 2 kids with Tay-Sachs. So how are we going to come up with these numbers? So the way we're going to figure out these numbers to place in front here is using this structure here, which is known as Pascal's triangle. On an exam, this will be provided for you. So I'll look at this triangle here, and then I'll count the number of lines I have. So I have 1, 2, 3, 4, 5, 6 lines to fill in. And then I'll look across here and find the row that has 6 numbers. 1, 4, 6, 4, 1, that only has 5 numbers, but 1, 5, 10, 10, 5, 1 has the 6 numbers I need. So now I'll put a 1 here, a 5 here, a 10, a 5, and a 1. And so what this tells us is to have 5 healthy kids, there's only one way you could do that, and that is if each of the kids were healthy. There's 5 different possible ways that you could have 4 kids healthy, 1 kid not healthy. 10 possible ways for this combination, and so forth. Now we can solve our problem. It's taken us a while to get here, but now we can solve it. Because remember, our original problem was what's the probability of having 2 kids with Tay-Sachs and 3 healthy? And so that's this one right here. We want to solve this equation, 10 times p to the third times q to the second. I think we all have enough room down here to do so. So to do that, we go 10. The value of p is 3/4. So that's going to be 3/4 to the third power. And then q squared is 1/4 squared. Now I want to back up. Again, I should have mentioned this before, but each of these events can occur. They are mutually exclusive, though. That's why we add them together here. If we calculated all of this out, it would equal 1. Okay, let's come back here. Now let's calculate this. 10 3/4 cubed, 1/4 square. So this is going to be 10 times, and remember, we always do the exponents first. So this will be 27/64. And then this will be 1/16. We multiply this through, and we get 270 over 1024. So the probability of having 5 kids, 2 with Tay-Sachs, 3 healthy, from these 2 parents that are heterozygotes is 0.26. There will, without a doubt, guaranteed be a question like this on the exam. It won't be just like this. It won't be 5 kids, 3 and 2. It'll be some variation that you will have to apply this rule to tell me this probability. Okay, now let's move on to our chi-square analysis. Now in lab, you'll probably get more practice using a chi-square, but I wanted to take a little bit of time and talk about chi-square with you now. So you have this as an aid for lab. It's also fair game on an exam, and I can also tell you that without a doubt, you will have a chi-square problem on the exam. Now remember what we said, is that geneticists will first make a prediction, do the experiment and gather their observed data, and then they will compare their prediction to their observed data. We always expect some deviation between observed and predicted. So if we predict a 3-to-1 ratio, our observations are not likely to be exactly 3-to-1. But the question is, how much of a deviation is okay for a prediction, or we might say hypothesis, to be supported? We also know that deviation will be less as sample size increases. So if I toss a coin 8 times, my prediction would be that I would get 4 heads and 4 tails. However, I suspect my deviation is going to be quite large with only 8 tosses. If you want, go ahead and toss a coin 8 times and see how close you get to a 1-to-1 ratio here. However, if I took that coin and tossed it 1,000 times, I don't recommend doing that. That'll take you too long. Our prediction will still be a 1-to-1, 500 heads and 500 tails. After flipping it 1,000 times, our observed results will probably be much closer to this 1-to-1 ratio as opposed to flipping it only 8 times. We will use our chi-square analysis to see if our prediction of 1-to-1 matches our observed. When we do a chi-square analysis, or whenever you do a chi-square analysis, you have to establish a null hypothesis. A standard null hypothesis might be something like this. There is no significant difference between predicted phenotypes and observed. With that in mind, any difference that we see, if the null hypothesis is supported, any difference we see will be due strictly to chance. You flip a coin 100 times, if there's a deviation, it's just chance. It doesn't always follow. There's always a degree of chance we have to consider in analyzing our results. So let's work through a problem. In this problem, we're going to deal with a monohybrid cross. We're going to take a big B, little b, and we're going to cross it with a big B, little b. Let me define what B is. In this problem, B is an allele in cats that generates black fur. And little b is an allele in cats that generates gray fur. So big B and a big B or a little b is going to give you black fur, and a little b is going to give you gray fur. So they do this cross, and we would have predicted that we would get 3 black, 1 gray. And if you don't see how we came up with these numbers, do a simple Punnett square on the side of big B, little b times big B, little b, and you should see 3/4 as being big B, big B, big B, little b, and 1/4 as being little b, little b. So this is our prediction. What they got was 30 black cats and 20 gray cats. Now the question is, does this follow a 3-to-1 ratio? And if it's not exactly a 3-to-1 ratio, which it's not, but is that deviation, that difference between these two, significant, or is it not significant? If it's not significant, then it's just due to chance. But if this difference is significant, then we have to conclude something else is going on here. So we're going to perform a chi-square. But it's important for us to think about a chi-square, what it does for us. Chi-squares only tells us if the probability that the difference between observed and expected is due to chance. So this is what a chi-square tells us. Chi-squares do not tell us if the experiment was done correctly. It also does not tell you if results are correct. It's just evaluating the results. Okay, so to do a chi-square, there are a few steps we should think about. The first is establishing the null hypothesis. What is it that you're predicting? Then calculate the expected results. Then, after you perform the experiment, complete the chi-square, and then determine if you will reject or fail to reject. We never say accept. We just say we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. Let's begin by establishing our null hypothesis. And so for this, we might say the deviation between our expected and observed data is due to chance. So there's no difference between expected and observed. That is our null hypothesis. If we end up rejecting this, then we'll have to come up with an alternative hypothesis. Okay, so what is our expected results? Well, in our problem, we know we have 50 progeny. That's given to us in the problem. And we know because of our Punnett square prediction, we would expect 3/4 to have the big B phenotype or have the black fur, or the gray fur would be 1/4. And so we would expect then that 3/4 times 50 is how many black furred cats we should have. So 3/4 times 50 is 37.5. Sometimes when people do this and you get a 0.5, they think they might have done it wrong because you can't have half of a cat. These are just expected data. We're not saying that you would actually see a half of a cat that is black and a half of a cat that's gray. Then our prediction for gray cats, so this is black cats, so we take 1/4 times 50, and that is 12.5 gray cats. Okay, now we can plug these data into our chi-square. Our chi-square equation is this. So chi-square is equal to the sum of observed minus expected squared divided by expected. In this, O is equal to observed, E is equal to expected, and chi-square is the sum of calculated values for each category. So to do these, I always like to set up a table where we have traits here, we have observed numbers here, our expected here, and then we'll do a calculation of observed subtract expected, and then we'll do observed subtract expected squared, and then over here we'll do observed minus expected squared divided by expected. All right, so let's get started with this. So our traits are either black cat or a gray cat. Our observed from the problem tells us that we see 30 black cats and 20 gray cats. Our expected, as we just calculated on the previous slide, is 37.5 black cats and then 12.5 gray cats. These should both equal to 50. So again, 37.5 comes from multiplying 50 by 0.75. 12.5 comes from multiplying 50 times 0.25. Do not multiply 30 by 70% to get this number, because that would be wrong, or 20 by 25% to get this number. Always multiply it by the total number. Then 37.5 subtract the expected. That will be minus 7.5. 20 subtract 12.5 will be 7.5. Now we square that. And if you square 7.5 or negative 7.5, you get 56.25. 56.25 divided by expected. So 56.25 divided by 37.5 gives you 1.5. And 56.25 divided by 12.5 gives you 4.5. I should have also wrote 56.25 here. We add these numbers up here at the end, and we get 6. This is our chi-square value. So now what are we going to do with this value here to determine if we're going to reject or fail to reject our hypothesis? We're going to use one of these tables here. You have one in your book. It'll certainly be supplied to you on the exam so you can use it. But you have to do a few things here. The first, you need to calculate your degrees of freedom. So degrees of freedom is calculated by taking your number of categories, subtract 1. For us, our number of categories is 2 because we have 2 categories, black and gray. Subtract 1 from that and you get 1. So we know by looking at this table here, we're only going to look at this top row here because that's where our degrees of freedom are. And then what you're going to do is in this top row, find out where 6 is. So we see 3.84, 5.0, 6.6. So we know that 6 is somewhere in between here. So I'm going to just circle all of this here. So we would say that the probability that the deviation is due to chance alone is greater than 0.01, but it's less than 0.025 because the number is right here. It's in between those two. I'm going to keep this table here, but I'm going to erase some space here so I can do some more writing here. So remember our chi-square was 6.0. Our probability that the deviation is due to chance alone is between 0.01 and 0.25. You could also think of this another way and say that the chance that this could occur is between 1 and 2.5%, though I like this way of showing it a little bit better. So a common probability that we use in chi-square analysis to determine whether or not we're going to reject or fail to reject a hypothesis is 0.05. So if P is greater than or equal to 0.5, then we say deviation is due to chance. And we fail to reject the hypothesis. Now let's consider the other option, and that is if p is less than 0.5, then we say that the deviation is not due to chance. And there's something else going on here. We need to come up with a new hypothesis to test, because we are going to reject our hypothesis in this case. So do we fail to reject, or do we reject our hypothesis? Our p-value is right here, and so it is less than 0.05. Since it's less than 0.05, we're going to reject our hypothesis. And our observed data, 30 black to 20 gray, is not consistent with our expected values. And so there must be something else going on. Now, we don't have to talk about what's going on in that quite yet, but next week we will start talking about non-Mendelian ratios. And this is going to fall into that category. And a bit of a spoiler alert, so you might want to hit mute if you don't want to hear this. But what's happening here is this is a classic example of a lethal allele. And so if you went back and redid this test, and you can do this if you want for fun, because this was loads of fun the first time, is redo it, but instead of a 3-to-1 ratio, do a 2-to-1 ratio. Okay, that's all I have for this podcast on probability and chi-square. If you have any questions at all, please make sure you come talk to me. If not, I will see you in class. Bye.